let us have a look at the characteristics of magnesium. It has an HCP crystal structure, hexagonal close pack, similar to titanium. The lattice parameters are given: a length of axis of unit cell parallel to the close pack directions within the basal plane. So this is a unit cell of HCP, and A is this distance, right? Between the central atom here and here also an atom is sitting. They are touching each other. If I draw these atoms with a realistic size, and that is too small, I make it a little bit larger, I will see that atoms are in contact in this direction. And this is the distance A, which we use in order to define the lattice parameter of magnesium and HCP metals. And this is the length C, right? So these values are given here, and we also we can calculate the ratio of C to A. Ideally, for HCP, we expect to have a value of 1.633. We could calculate that using knowledge of geometry. In case of magnesium, it deviates a little bit. And some people argue that this is responsible for the formability of HCP alloys. If we get values close to that ideal ratio, we could expect a better formability, right? That is one of the arguments, but it is not for sure. We know that in general, HCP metals exhibit a poor ductility. For titanium, the ratio is even lower, but in terms of ductility, I would say that they are kind of comparable, right? If you have a titanium alloy with a good ductility, probably we expect 10, probably 20% of elongation, and the same also kind of applies to magnesium alloys. There are indeed a lot of factors which play a role. For example, grain size. If we could get HCP material with a fine grain size, we could expect a better formability, because with a single crystalline HCP, we must have a favorable orientation to activate glide systems. If I assume that this is my HCP and this basal plane, if I assume that this basal plane is the only glide plane, if this basal plane is perpendicular to the direction of loading, if I load it in this direction, I'm not going to activate any of the slip systems because this plane is perpendicular to the direction of loading. I cannot create any shear stress on this plane parallel to the slip direction. If I want to activate a slip system, the slip system must feel a shear stress caused by this normal stress. But this normal stress is not able to create any shear stresses, and I'm not going to activate any slip systems. The same applies if I'm applying a load in this direction, right, within the basal plane. Within the basal plane, if I put a stress, I'm not going to activate any of the slip systems because I'm not creating any shear stress on this basal plane. So if I manage to get a fine-grained material, I could probably get formability from the neighbor grain, right? The chances of getting a compatible deformation of my component is going to be higher. Good, but even with very ductile magnesium alloys, I think 20% would be a very high elongation, something we could be really proud of if you're talking about magnesium. Good density is very low, and this is one of the main advantages of magnesium. This is actually the driving force for the development of magnesium alloys. It is even lighter than aluminum, and it is kind of filling the gap between aluminum and plastics. A lot of plastics have densities of the order of 1 gram per cubic centimeters, and here we get something between that of plastics and aluminum. So in applications where plastics are not satisfactory anymore, for example, because they have a very low stiffness, the elastic modulus of plastics barely exceeds 10 gigapascals. I'm not sure if there are plastics which are reaching that level. A lot of times we are talking about values between 1 to 5 GPa, whereas with magnesium, we get a higher value. That value is indicated here. So it offers a much better stiffness compared to plastics. And also in terms of temperature capabilities, if you have a thermoplastic polymer, you take it to 100 degrees Celsius, you could assume that it loses strength dramatically. Right? So the stiffness goes down, it goes much below 1 gigapascal, and the capacity of that in order to carry a load decreases a lot. With magnesium, we got a melting point very close to that of aluminum, only about 10 degrees lower than aluminum. It makes it easier to cast magnesium alloys. We could use tools out of steels in order to process aluminum alloys. If you want to make a mold in order to cast magnesium, we could think of a metallic mold out of steel. So we don't have to go necessarily to ceramics. Indeed, magnesium alloys are also cast in ceramic, in sand molds, but we got the option to use steels. Then in terms of elastic modulus, it offers a value lower than that of aluminum. With aluminum, we are happy with 70 GPa. We use 70 as an average elastic modulus for a polycrystalline aluminum alloy. And we know indeed that GPa, that elastic modulus, is orientation dependent. So it matters if I'm loading my grain parallel to, for example, 111 direction or parallel to 100 direction. And if you're talking about HCP, we have to use Miller indices with four digits. So it matters, for example, if I'm loading parallel to 11 bar 20 that would be the closed pack directions in HCP, or if I'm loading parallel to the C-axis, right? I'm going to get different values. But on average, if I'm dealing with a polycrystalline material, for polycrystalline materials, we could use an average value, which is in this case somewhat lower than that of aluminum. So it's going to experience a larger deflection under load. The UTS values are also somewhat lower than those of aluminum. With aluminum alloys, there are alloys where we can aim for UTS values of 600 or probably even 700 megapascals. Whereas here, the limit is much lower, right? We are talking about 350 as an upper limit for magnesium alloys. And this is something to achieve if we are thinking about an alloy where we can take advantage of mechanisms such as precipitation hardening. The formability of magnesium is very low, in particular at room temperature. If you want to do rolling or forging, instead of doing that at room temperature, it makes sense to go to higher temperatures, where we can also get some creeping thermal activated mechanisms in order to get a better formability. Another drawback of magnesium alloys is corrosion resistance. It is not as corrosion resistant as aluminum alloys. It is probably somewhat better than RN. It depends also on the environment. But if you are talking about a humid environment, we could expect magnesium alloys to corrode, right? So they are susceptible to corrosion, especially if we are talking about wet environments. There are techniques, there are strategies to enhance corrosion resistance, but in spite of those strategies, we could not expect them to be as corrosion resistant as aluminum alloys. So if you take a piece of aluminum, a piece of magnesium, and you put some vinegar on the surface of both alloys, you could identify them. So you see formation of bubbles on the surface of magnesium, whereas with aluminum, there is practically no reaction, right? So it is easy to distinguish them based on their corrosion resistance. This is probably related to the nature of the oxide which we form on the surface of magnesium. It is not as dense as that of aluminum, and it's going to continue to corrode. Another issue with magnesium is its susceptibility to burning. It can burn if we create a spark. If temperature goes up, raising temperature could result in spontaneous burning of magnesium alloys, right? So this is also something to be aware of. If someone wants to put magnesium in an aerospace application, then it is important to also check that those alloys are kind of not very flammable, right? So there are special alloys which are less susceptible to burning, and those could be good options for applications where there is a risk of formation of a spark or exposure to high temperatures. Another problem associated with processing of magnesium alloys is related to the high oxidation tendency of magnesium, not only in the solid state, but also in the liquid state. If regions of surface of molten magnesium are exposed to atmosphere, to air, they are going to fire, right? They are going to burn. And it makes it necessary to take special measures in order to avoid burning of magnesium melts. There are special atmospheres we have to put on the surface of molten magnesium to avoid burning. There are special salt fluxes, for example, which help to form gases which contain components such as SO2 or SF6 or other sorts of gases, which could cut the contact between air and magnesium melt. Otherwise, it's going to burn. And this is one of the challenges associated with magnesium alloys. If you want to cast them, you also have to create a protective atmosphere in order to avoid contact with air. Or you have to put special fluxes, some solid materials, you can pour on the surface in order to create these protective gases. A lot of times they are dangerous gases, and people who are working in these environments need to have a special safety equipment, right? There are some concerns about health issues related to people working in the magnesium industry. Good. Here are a few examples of magnesium alloys. High pressure die casting is a very common technique in order to make magnesium alloys. A lot of casings where we need to have a case, and it doesn't have to offer a very high strength. Then we could think about the lightweight potential offered by magnesium alloys, or camera cases, another common application where we could achieve lightweighting. If you want to avoid plastics, if you want to avoid heavier metals, steels, stainless steels, or even aluminum alloys, we could switch to magnesium. And some other applications, laptop cases could be made out of them. And also in the automotive industry, there are some concepts where the engines are out of magnesium instead of cast iron. Cast iron is very heavy nowadays. the industry is using aluminum alloys. It's a very common solution for this application, but one could also think about using magnesium and enjoy the lightweight potential. Good. Indeed, not all portions of the engine are out of magnesium. The liners here, which are in contact with pistons, they need to have a very high wear resistance. And for that purpose, we are using hyper-eutectic aluminum silicon alloys as liners in cylinders. So it is a hybrid concept. The outer layers, which are not heavily loaded, they could be out of magnesium. They could also be out of aluminum alloys, and the liners, where we require a high wear resistance, a higher hardness, they could be made out of high silicon hyper-eutectic aluminum silicon alloys. Good. Some other applications of magnesium as element is to put them in aluminum alloys. We discussed some series of aluminum alloys where magnesium was playing a very important role, 5000 series. Right? If there is a rise in the application of 5000 series, it means that we require to also produce more magnesium because we need the application of aluminum alloys is much higher than that of magnesium alloys. We will compare the size of both industries. It becomes obvious that the amount of aluminum produced annually is much higher. We got a factor of something like 70 times higher than the application of magnesium alloys. So if there is a rise in the application of 5000 series, it has consequences for the need for magnesium alloys. It is going to also influence the price of magnesium, right? Some alloys of 5000 series, wrought alloys, they contain up to 5-6% of magnesium. And that is one of the major uses of magnesium. Also, the cast iron industry uses a lot of magnesium, and that is for the purpose of changing the morphology of graphite from lamellar to more or less round. If we want to get ductile iron, we have to change the morphology of graphite lamellae. Instead of getting lamellae of graphite, we want to have more or less round graphite particles, because by that we could reduce the stress concentration. So here, if we got lamellar graphite, we got regions with a very high stress concentration. Load is locally, or stress is locally very high, and it's going to create a dangerous situation. We could start cracks. Whereas we could change morphology of graphite to round by addition of a little bit of magnesium, right? Magnesium in small quantities could do the job and make cast irons more reliable. If we got a ductile iron, and ductile iron are the ones where we are adding magnesium, we call them ductile cast iron, and these are simple cast iron, so cast iron with lamellar graphite. Good. Right, these were some important properties of magnesium and its alloys. Let us review very briefly methods to produce magnesium. There are a number of methods. There have been a few developments, but I'm going to just cover two of the important methods of producing magnesium for an idea of how we can get magnesium. What are the sources of magnesium alloys? So magnesium could be produced from seawater, because seawater has a magnesium content of 0.13 mass percent. Right? And that is a huge amount. Just think about the volume of seawater available to us. We can extract a lot of magnesium from seawater. And the method in order to get magnesium from seawater, and I think this is the main source of magnesium nowadays, right? Processing of seawater. We need to get magnesium oxide from seawater to mix it with chlorine. So chlorination is the first step. It is kind of similar to what we did with titanium. With titanium, we were aiming for titanium tetrachloride, right? And in this case, we are aiming for magnesium chloride, MgCl2, and that could be achieved by addition of chlorine at a high temperature. The tendency of magnesium for chlorine is very high. We could strip oxygen from magnesium oxide, because these are very stable oxides, but by exposure to an atmosphere where we got chlorine, we could strip oxygen from magnesium. Right, and carbon could help to increase the temperature. It is not a major player in the process. We see that carbon is going to react with the oxygen, which gets free, we get CO. Major player is here chlorine, which helps to get MgCl2, which is then processed in the second step, and that is electrolysis. Similar to what we do with aluminum alloys, there we are using aluminum oxide, right? Not aluminum chloride. There we are using oxide, and we are using cryolite in order to reduce the melting point of aluminum oxide. That was the Hall-Héroult process for the production of aluminum alloys. Here there are some similarities, but instead of using magnesium oxide, we are using magnesium chloride, right? So what we produce here will be used in the second step in an electrolytic cell, where we use temperatures like 740 degrees Celsius, very small voltage, in order to produce magnesium at Rn cathodes. Right, we are going to use cathodes. This some out of Rn. It is not out of graphite, like is the case with aluminum, but our anodes are again out of graphite, right? And there we are going to get chlorine, gaseous chlorine. Good. This is a method to obtain, one of the methods to produce magnesium, for instance, if you're using seawater as the initial source. Now, if you would like to produce magnesium from the crust of the Earth, because we also have access to sources of dolomite, for example. This is a mineral which is carbonates of magnesium and calcium, right? And also magnesite. It is a carbonate of magnesium, which is available to us from the Earth crust, right? If we want to use this source, what is available to us is to use direct thermal reduction of calcined sources like dolomite, right, or magnesite. How do we do that? If they are calcined, they are heated up to get rid of CO2, right? We can eliminate CO2 and we could convert this to MgO, right? And also here, CaCO3, if you're exposing them to high temperatures, they get calcined, right? So they lose their CO2 and they could participate in a reaction, which we could summarize in this form. We could summarize the entire reaction. We are using dolomite. We are bringing that into contact with silicon at a very high temperature. By that, we could reduce magnesium. We get magnesium reduced, but due to these high temperatures, it is in the gaseous form. We get magnesium as gas, and this is the byproduct of reaction, right? So we get gaseous magnesium, which can be condensed by contact with water-cooled sleeves. We could get cylinders, which are cool. Gas goes through, and as the temperature of the gas decreases, magnesium gas, it is going to condense, and we get magnesium, right? So this is one of the ways in order to produce magnesium. Therefore, there are two methods, depending on the source, or two major methods. There are alternatives, but again, we are using either magnesium from seawater or from the Earth crust. Let us have a look at the numbers, how much magnesium is produced, and a little bit of history. Magnesium was produced around in the 19th century. In the early 19th century, there were a few efforts to strip oxygen from magnesium because it was a hard task, right? Due to the very high affinity of magnesium for oxygen, it was hard to isolate magnesium, to separate oxygen from magnesium. Towards the end of 19th century, there were almost 10 tons of magnesium produced annually, right? So these are annual numbers, which are very small quantities, right, compared to the productions nowadays. Towards the end of this First World War, there were almost 3,000 tons of magnesium produced annually. Then right after this First World War, there was a reduction in the amount of magnesium produced. So it has been subject to a lot of fluctuations. There has been a lot of ups and downs with magnesium. Right after the First World War, it went down, and by the time of the end of the Second World War, we were producing almost 300,000 tons of magnesium annually. So the numbers increased a lot after a decline in the production. But now, if we look at almost 55 years later, right? 55 years later, production was still of the order of 400,000 tons. So it is not a huge increase. It is not a dramatic increase in the production of magnesium. And in the time in between, there were, as I mentioned, a lot of ups and downs. People realized the difficulties, prices were very volatile depending on the availability, right? There were a lot of changes in the price of magnesium, and that influenced the market dramatically. And there were also some other developments. There were developments of high-strength aluminum alloys, and it is hard for magnesium to beat aluminum, right? In a lot of aspects, we think about corrosion resistance. We think about the possibility to produce them by die casting. Both of them are easy to melt and produce by casting. In terms of stiffness, aluminum is even better. So it is really hard. That is one of the challenges which the magnesium industry is facing, right? It is hard to compete against aluminum alloys. And there were also some developments based on plastics and composite materials, where people started to put carbon fibers or glass fibers in plastics and increase their strength and their stiffness to levels comparable to those of magnesium alloys. So it increased to 400,000 tons. And then from then on, I think from around this time, or from 2010, there was a sharp increase in the production of magnesium. And I think that was because of the huge production coming from China. I got the values from 2010 up to Corona times, right? There was a rapid increase in production of magnesium, and most of that was coming from China. I think even now, China is producing, right? It's mentioned here, 80% of magnesium worldwide. So it's controlling the industry. In Europe, it is not economical to produce magnesium. You don't see magnesium shops. They are using probably secondary magnesium alloys. If it's at the end of its lifetime, they could remelt it and produce another alloy. But we are not seeing production of primary magnesium in Europe. As far as I know, nowhere in Europe I heard in Turkey they started to make some shops, but I think it is still producing in very small quantities. And also Russia is a producer, right? But if you just consider the amount of magnesium produced in the post-Soviet states, Russia, Ukraine, and the other former Soviet Union states, it is accounting for only 10% of the market, and 80% coming from China and 10% from the rest of the world. So it is controlling developments in the magnesium industry almost exclusively. And this decline here, I don't know, perhaps it is related to the pandemics. Good. So that was with the size of the market. So if we look at the numbers nowadays, we could assume that we are getting almost 1 million tons of magnesium annually. Let us put this into perspective. Let us make a comparison with that of titanium. With titanium, we are getting almost something like 0.2 million tons, right? So somewhat lower of titanium alloys. And with aluminum, we are talking about values like 70 million tons of primary aluminum. And there is also a lot of secondary aluminum. So secondary aluminum is the one which is getting recycled. Think about aluminum can industry, right? They are recycling a lot. And if I just consider the primary aluminum, it is something like 70 million tons of primary aluminum. So we could see the comparison. We discussed aluminum a lot more than the other alloys, and it is also for a good reason, right? Size of the aluminum market is much larger than those of the other two elements. If you think about the market value, and if you think about the high price of titanium in terms of the market size, we could say that titanium is even larger than magnesium alloys, right? Because in terms of price, titanium on average is probably something like 5 to 10 times more expensive than an average magnesium alloys, right? So if you put a factor of 5 to 10, we see that the size of the titanium market by value, I would expect it is something like double the size of magnesium industry. Good. Now let us have a look at plasticity of magnesium alloys. We got the issue we discussed with titanium, also with magnesium alloys. It is HCP material. The number of glide systems are very limited. And if we have a look at the critical resolved shear stress in order to activate different glide systems. So CRSS indicates the critical resolved shear stress. CRSS. This is the stress required to activate a particular glide system. For instance, if I'm thinking about a HCP, basal planes contain some glide systems. For example, here I can activate glide systems on this plane parallel to that direction, right? That would be one of the glide systems available in HCP. But we can see already the difficulty. All these sorts of planes, and these planes have Miller indices 0001 or 0002. Right? These are basal planes, and they are all parallel to one another. So it is hard to get good plasticity because we are always sliding our material on parallel planes. And this is not a favorable situation in terms of formability. There are also possibilities to activate other slip systems. For instance, we could consider pyramidal planes. For example, if I connect these 2 points to these 2 points, I can visualize a pyramidal plane. Right? And I could either, again, get slip in this direction. This would be A type of slip because the slip is happening within this basal plane. So we call this A type of slip. Or I could activate probably glide system in this direction. And that would be a C plus A type of glide system. Right? So these are a bunch of different possibilities for the plasticity of magnesium alloys. If you compare, for instance, this pyramidal plane with the basal plane, it is much easier to activate glide systems on the basal plane. And that is something we could understand from this chart, from this curve. It shows the critical size of shear stress, which we have to produce on glide planes. For instance, if I'm thinking about basal plane, right, on this plane, I would like to activate the glide system, and I would like to get a shear tau, shear stress by putting an axial stress. I'm loading my material, for example, in this direction. This is the direction of sigma. I'm putting a uniaxial stress. And because of that uniaxial stress, I'm producing some shear stress. If this shear stress reaches a critical value, then I could activate this glide system. Now, if this critical value is high, it is hard to activate glide systems. It is low, then I could easily activate it. Therefore, the values we are looking at here indicates how easy it is to activate different glide systems. For example, glide system of basal type. This is glide on basal planes with slip system parallel to 1, 1, 2, 0 directions, to the closed pack directions. And we can also see values for prismatic slip. Prismatic slip happens on these sorts of planes. This would be a prismatic plane, and I could get a slip, for instance, in that direction. That would be prismatic plane, and that could be the direction of slip. In that case, it has no component parallel to c-axis. I could call this a type of slip, right? And this is actually what is meant by blue color here. This is prismatic, right? I put orange there, but I'm talking about the one here marked in blue. And for pyramidal type of slip, I put blue here in my schematic for one of those pyramidal planes. The Miller index for this one, for the blue one, is what kind of Miller index do we expect here? Let us see. So I think this is 1, 0. It is cutting C at 1, so we get 1 here. Sorry, we get 1 at the end, and here we get -1. So the one I drew there, it should have this sort of Miller index, right? That is a Miller index for this type of plane, pyramidal plane. Good. They could get activated, and we see values for different types of glide systems. It is also possible to get tweening in magnesium, right? And there are also some tween systems. For instance, I could get tween on this pyramidal plane. I could get tween exactly on the one I drew here, right? This could also, the blue one could also act as a tweening plane. I could get a reflection of crystal structure on these planes. I get a mirror symmetry, and I'm able to get tweens there. So if we compare the values, we see that the value for the activation of basal slip is much lower than those of other slip systems. It is much easier to get to activate basal slip compared to the other ones, but with basal slip, the number of slip systems are very limited. We can only get 2 independent slip systems, right? And that means that we cannot freely change the shape of my material. I got a hexagon here. This could be my magnesium grain. I could only make planes parallel to basal plane slip against each other. I cannot flexibly change the shape of my component because of this restriction with the number of glide systems. There is a rule, plasticity rule, saying that in order to freely change the shape of a part, of a component, we need to activate at least 5 glide systems. And we cannot do that here. It's very hard because the other glide systems have very high critical values. We need to put a lot of stress, high shear stresses, in order to get activation of those glide systems. So practically, they are impossible to activate, and that restricts the ductility of magnesium alloys. As I mentioned, we could do measures like grain refinement in order to get a better ductility with magnesium alloys, but that is also that it makes it necessary to get a wrought magnesium alloy. A lot of magnesium alloys are cast alloys, majority of them, and we got no chance in order to do grain refinement. Good. Let us go further and have a look at the corrosion resistance of magnesium alloys. In terms of corrosion resistance, as also mentioned before, it is not performing well, and it has to do with the impurities. So impurities play an important role. Not that impurities are responsible for that, but impurities could make the situation worse. If we have some, for example, Rn could form some compounds which could play the role of cathodic sites, so regions with a higher potential, and they could accelerate corrosion of the matrix of magnesium, right? So if we have a matrix, so assume this is our macrostructure, this is a HCP matrix of magnesium, and we got some particles, and these particles are cathodic. They have a higher electrochemical potential. Then we expect that regions of matrix around them are going to corrode. So this is a cathodic particle. Cathodic particle means that it has a higher electrochemical potential. It causes corrosion of the matrix, right? It is as if it is something like the concept of sacrificial anodes. We got 2 metals with different electrochemical potentials. The one with the lower potential starts to corrode. And this is one of the challenges associated with magnesium alloys. If there are impurities, we get a lot of cathodic sites, which decrease the corrosion resistance of magnesium alloys. Here are some results showing the corrosion resistance of magnesium in a solution containing 3% of salt. As soon as the concentration of Rn exceeds this critical level, we are going to see a huge increase in the corrosion rate, right? Corrosion rate goes up dramatically as soon as this critical limit is exceeded. there are some strategies in order to cancel out the role of these detrimental elements. Iron is an element which could come, for example, from the die materials. If we are producing magnesium by die casting, the tools which we are using, the dies we are using, are out of steel, and they could introduce some iron to the surface of components out of magnesium, right? So and also during handling of magnesium alloys, a lot of tools we are using are out of steel, and we could not exclude the presence of iron. What we could do against this is to add some manganese. Manganese is an element which is going to help and kind of make compounds containing iron which are not as cathodic as the ones which could form without manganese. So by adding manganese, we could change the nature of these precipitates so that they are not very cathodic, and by that we could enhance the corrosion properties. So iron is not the only element. There are also other alloying elements. Nickel above a critical level, and this critical level is extremely tiny. If the amount of nickel exceeds this level, or copper is present above this percentage, more than 0.13% of copper, we are going to see a huge degradation of corrosion resistance. So we need to also have a good control of impurities. And if they are present, then we have to think about methods to combine them, to convert them to other components which are less detrimental in view of corrosion properties. Good. Now let us have a look at the designations of magnesium alloys. How could we call magnesium alloys? For that, there is a American standard. So American Society of Testing on Materials, ASTM, has proposed this designation, where we could use up to 4 different positions in order to designate magnesium alloys. Here's an example, right? This is a designation where we see positions 1, 2, position 4, and we are going to see what they mean. Positions 1 and 2 are giving us information about rough chemical composition, at least about the main alloying elements in magnesium alloys. So if you're putting aluminum as alloying element, we use the letter A. So A represents aluminum, B represents bismuth, C represents copper, and for the other alloying elements also, there is a particular letter. So alloying elements are represented by letters. And sometimes groups of alloying elements, for example, rare earth elements, get the letter E. So we combine them. If we got a scandium, for example, then we could use this letter in order to represent it. And also other rare earth elements. Neodymium, for example, belongs to one of to those elements, but we could just sum them up and collectively refer to them as with the letter E. We use letters to represent alloys, main alloys, or main alloying elements, and we could represent 2. A lot of times we represent 2 of the principal alloying elements, but we could also refer to more elements. There are also designations where we show the chemical composition of the 3 most important elements. The examples I'm showing here are the ones where only 2 main elements are considered. For example, AZ63, it indicates that this alloy contains element A, and A indicates aluminum, and it also has element Z, and Z is referring to zinc. So Z63 is referring to an alloy which contains these 2 elements, and these 2 numbers which are following are given information about the rough or rounded percentage of those alloying elements. So this tells me that this alloy has 6% of aluminum and 6% of zinc included. If I look at this one, AM20, it has 2% of element A, and A is aluminum, and it has almost 0. Here we see 0, but this element is present, but in amounts less than 0.5%. If it were more than 0.5%, we could use here, we could use 1, but this element is present, but in an amount less than 0.5%. What is that element? Element M, if you refer to the table, is manganese. So we could assume that there is, we will know that there is some manganese included in this alloy. Right, and also for the other ones, this one is one of alloys which is used in the medical industry, and I will show some examples of the use of these alloy. W represent yttrium, and E is referring to rare earth elements which are there. Good, and concentrations are also indicated here. Good, so this is the way we can fill positions 1 and 2, and these 2 positions are always filled. We could also have extra positions. Position 3 could be there, and this indicates this is a way to distinguish those alloys which in terms of amount of main alloying elements have the same amount, but they have been new developments. For example, initially people thought 6% aluminum, 3% of zinc would be a good combination, but then they changed the amounts of other alloying elements. So probably the first development didn't have much manganese, then they decided to put some manganese to enhance corrosion properties, and then there was another modification, and every modification was designated with a letter. For instance, the first development, the first standard grade could be referred to as A. if there has been a layer development, it takes the layer B, right, in the order of development. Or the order of standardization, right? The newer developments get letters down in the alphabet. Good. So that was with the position 3, and position 4 is a familiar one. This is something we have discussed in the context of aluminum alloy. So I'm not going to go through that. Perhaps some examples here. It indicates temper conditions, and T6, as we learned in the context of aluminum alloys, indicates artificial aging. So this applies to an alloy which is capable of precipitation hardening. We do a solution heat treatment, and afterwards we expose it to higher temperatures to get precipitates and potentially use precipitation hardening. In that respect, it is similar. If you think about temperatures for solution heat treatment and for aging, we have to refer to the applicable phase diagram. Solution heat treatment is done in the single phase range. Then we quench it down to get a supersaturated solid solution, and then we need to do aging. And the temperatures we use for aging are kind of similar to those with aluminum alloys, because in terms of melting point, they are very similar. So if you do the math and calculate the temperature, where we are at almost 40% of melting point, we get similar values for aluminum and magnesium alloys. So in this case, also, we could think about temperatures between 100 and 200 degrees Celsius as being suitable temperatures for the aging of magnesium alloys. Good. T4 indicates natural aging. What else did we discuss? We discussed H tempers. H tempers apply to strain hardenable alloys. You get an alloy, you do some deformation, and depending on the amount of deformation, if you apply, for example, 20% of cold rolling reduction, you could use H12. If you're putting 75 to 80% of reduction, then you could use temper H18, and so on, as discussed in the case of aluminum. Good. Here are some examples to just give you an impression of chemical composition and also a comparison of cast and wrought magnesium alloys. So here we are looking at some alloys, and for both of them, for wrought ones and for cast ones, we use the same ASTM designation. The one we reviewed is applicable to both of them, right? Doesn't matter if it's cast or if it's wrought. AZ63 gives us an idea about chemical composition. We can also confirm that it has 6% of aluminum and it has 3% of zinc, and some manganese is there. We could assume it is related to corrosion resistance. If iron is there as impurity, it could kind of scavenge and remove iron out of the system or make it less dangerous in view of corrosion resistance. Good. Then some tensile properties, if they are produced by casting, they are not as high quality as wrought products. So if they are produced by high pressure die casting, we know that they suffer from porosity. Liquid metal is entering cavity at a very high velocity, and that could result in the formation of porosity. So gases could enter the melt, they get entrapped, and by that we get a lot of gas porosity. So that is one of the drawbacks of cast parts, especially if you are using high pressure die casting. This is one of the concerns. Good. So in terms of strength values, we get an idea about what kind of values we expect. These are the proof stress or yield strength. The values of the order of 100 megapascals for these aluminum zinc alloys. I didn't show the entire table. Indeed, it was a very long table, and I thought we could just briefly discuss these important alloys. These are the most important alloys of magnesium, those which contain aluminum and zinc. And this is by far the most widely used grade of magnesium, which contains something like 9% of aluminum and 1% of zinc included. And the properties we could get with that grade, right? If it's as cast, if we do different tempers, right? T4 natural aging, T6 artificial aging, we could adjust the values. And if you look at the elongation of cast alloys, so the highest value I'm reading here is 5%, right? So we could be happy with values of the order of 5% elongation. It is not much. If you compare it with steel, with a structural steel, you test it, you get 25% of elongation, right? And it gives you a higher strength values in terms of yield strength. You probably get something like 200 megapascals. Right? For example, if we are looking at the grade S235, so this is a structural steel which gives us a yield strength or proof stress of 235 megapascals. And in terms of UTS, it is even higher, right? It might give you something like 500 megapascal of UTS, right? So these are values we could get with steels. They offer a higher strength and also a higher ductility. As I said, with a grade like this, you could expect 20% of elongation with a ferritic steel. And if it's an austenitic steel, you could aim for 50, 60, 70% of elongation, much higher ductilities. Good, that was with cast alloys, and here are some numbers for wrought alloys with a higher quality, with less porosity, especially if they are forged products. These are considered very high quality ones. You don't get porosities, and we get a lot of grain refinement due to the production, right? Hot deformation. And in this case, the strength values are higher, right? We see values up to 200 for AZ types of alloys, and tensile strength up to almost 300 megapascals are achievable. And we are also getting better elongations. Right? They are more costly. Processing is much more difficult compared to die casting, where within a second or within a few seconds, you get your part out, right? Especially with magnesium alloy, they lose their heat very quickly. If you compare them with aluminum alloy, the time in order to solidify a part out of magnesium is shorter than that of aluminum alloys. Aluminum alloys have more heat, right, in the liquid state, and it takes longer for them to give up that heat, to transfer the heat to the metallic mold, and it takes longer for them to solidify. Whereas with magnesium, solidification times are even shorter. You could get an even higher productivity if you aim for high pressure die casting, right? But we also saw the problems of high pressure die casting. One of them was you have to produce a part in a very high quantity, because design of the die is going to be very expensive, right? Design of the tools and the dies. And we should also consider that those parts could have a high porosity. Maybe they are leaking kind of alloys. They're transparent to gases, right? And these are some of the issues to keep in mind if aiming for die cast magnesium parts. Good. Right, as I mentioned, these AZ types of alloys are very important ones, the ones which contain aluminum and zinc. Let us see the function of these alloying elements. What happens if aluminum and zinc are there? By addition of aluminum, we could expect solid solution hardening. This is something which we expect from alloys. We are mixing two metals, and by that, we are going to get a change in the strength values. And here, aluminum is effective. It makes these alloys stronger. If you are thinking about an alloy AZ, for example, 80, it has 8% of aluminum, so we are almost there. And we have increased the yield strength by how much? We are going from something like 30 to around 80. So we are getting an increase of 50 megapascals in the yield strength by putting aluminum. If you're also adding zinc, then we could expect some additional strengthening. There are alloys like AZ93, right, where we are putting 3% of zinc. And there are also other alloys, not the AZ series, where concentrations of zinc are even higher, right? So that is also very efficient in increasing the strength of magnesium alloys. Good. And we could also have a quick look at their phase diagrams. What happens if we put aluminum in magnesium? So this is the most important alloying element, aluminum. It makes magnesium alloys somewhat heavier, but still, it's a better situation than when you're putting a heavier element like zinc or manganese in magnesium alloys. They are metals which are heavier, and aluminum would be a good option, right? So I could think about aluminum as not increasing the density of magnesium alloys dramatically. There are also options like lithium. We also consider that option with aluminum alloys. There were aluminum lithium alloys, which were very lightweight, and they were also giving us some precipitation hardening. And the same also applies to magnesium. There are a bunch of magnesium alloys, but I think it is not necessary to go to all those types of alloys, because if you just look at the volumes for production of those alloys, they are much lower. I would think that it is not necessary to go to those details. So it is enough to at least review this phase diagram, magnesium aluminum phase diagram. It looks something like this. This is pure magnesium, right? We have to look at it from right to left. This is the melting point of pure magnesium, 650 degrees Celsius. And as we start to put aluminum, we see a reduction in the liquidus temperature. So with 90% with 10% of aluminum, we see a reduction in the melting point. It goes to something like 600 degrees Celsius. So it makes casting of these alloys even easier, right? So they become more castable by putting aluminum. Then we see that the maximum solubility of aluminum in magnesium is of this order. So it's probably something like 13% of aluminum could be dissolved in magnesium at this temperature, at the temperature of eutectic reaction. This is the temperature where eutectic reaction happens, but majority of alloys which we are using are in this range, right? They are not in the range where they give us eutectic under equilibrium conditions. We might get eutectic under non-equilibrium cooling conditions, but just based on phase diagrams, we expect that by the time you reach this point, this is our solidus temperature, the alloy has fully solidified, and there is no liquid left in order to take part in this reaction if we do everything under equilibrium conditions. Under non-equilibrium cooling conditions, we could get some eutectic products as well. So this is the way the phase diagram looks like, and now we'll look at it more closely. To the left, we see the magnesium reach part of phase diagram. So this is pure magnesium, and we are putting aluminum up to 14%. So we are focusing on this corner of phase diagram, right? And right? The phase diagram is also indicated. The maximum solubility of aluminum in magnesium is something like 13%, 12.7%. And majority of AZ alloys have around 8 to 9% of aluminum. So I marked that region also. And let us see what happens to properties. And the properties considered here are U stands for UTS, ultimate tensile strength. P is standing for proof stress or yield strength, and E is indicating elongation. So by putting aluminum in magnesium, we could naturally expect to have solid solution strengthening. This is something we discussed before. No matter which method you are using, if you're using sand casting, even if that alloy is solution heat treated, we see an increase in the proof stress by increasing aluminum concentration. Then if you look at the UTS, right, here we see that UTS is also going up parallel to proof stress, but at some point we start to lose strength. UTS is going down, and the reason is related to the lower ductility. If we lose ductility, if the material breaks very early, right, if it breaks early, we cannot get a high UTS. Material has started to yield. If I refer to the stress strain diagram, material has yielded, right? But if it fractures early, we get a low UTS. It has a high yield strength or proof stress. But in terms of UTS, we read a small value if it fractures early. And if it's more ductile, we can work harden it more, and we could expect to get a higher UTS value. Right? So it matters how much elongation we are getting. So we could understand that this decrease in UTS is related to a decrease in elongation of this alloy. Right? And from this point on, we see a dramatic decrease in elongation, and this could be related to the presence of some non-equilibrium eutectic products. This is the sand cast part. We could expect that due to non-equilibrium cooling, some eutectic phases have formed. Right? If you're going here from right to left, we are getting some eutectic products which could decrease the ductility of alloys. This is because of the non-equilibrium nature of solidification. Good. Then we could correct that by doing a solution heat treatment. If we do solution heat treatment, those non-equilibrium phases will disappear. For instance, I take my alloy to this range, right? Or here, if I just refer to my diagram, to the one to the left, we could do a heat treatment there, do a solution heat treatment, and land in the single phase HCP region, right? Eliminate those non-equilibrium phases and get a better elongation. So elongation drops later, so we need to put higher amounts of aluminum in order to see a decrease in elongation, and by that the UTS values could remain high, right? So these are kind of correlated. If we get more ductility, then we could expect that the UTS is going to be much higher than the yield strength. Good. These are also some values. If you do further processing, further heat treatment, depending on what happens, if you are going to get, for example, some precipitous, if you do a heat treatment here, for instance, then we could start to get some precipitous or beta phase, and that could also influence mechanical properties. Elongation is going down, but in spite of that, we are getting a high UTS value. So the detail about the processing, it's just saying fully heat treated, but the exact processing was not indicated. But at least with this processing, we could get a high UTS value. It's getting a high strength alloy. Good. Now, one of the things about this alloy system, it looks like an attractive system to do precipitation hardening, but in reality, it is not attractive. In the context of aluminum alloys, we were saying that we could do heat treatment in the single phase alpha region, and alpha in the context of aluminum is FCC solid solution, then rapid quenching and heating up again. For example, in aluminum copper system, let me make it a bit bigger. Aluminum copper system. We were saying that up to something like 4.5% of copper could be dissolved, and we are in the alpha FCC range. Right? We could do a heat treatment in the single phase alpha region, solution heat treatment, then rapid quenching. By rapid quenching, we avoid the formation of theta phase, because here is the range of alpha plus theta, and theta is CuAl2 intermetallic. If we quench fast, we don't get these theta phases, intermetallics, and then we could do a subsequent heat treatment, aging, at, for example, 150 degrees Celsius, and by that bring out these GP phases, theta double prime, theta prime, and eventually the stable theta phase. And by that, we could adjust the mechanical properties. Now, in this case, it is not possible to get those intermediate phases. We directly get the stable beta phase, right? And beta has this chemical composition, and that is unfortunately not going to give us the strengthening. So it doesn't help much to think about precipitation hardening of this alloy system, although from phase diagram, one might get the impression that it's going to be an attractive concept. Good. Now let us review the methods to make magnesium alloys fine grained, because one of the challenges was the huge grain size, and huge grain size would mean that formability is going to be very restricted, right? There is just one orientation and everywhere the same orientation. And under some conditions, for example, loading parallel to the basal plane or perpendicular to a basal plane, I'm not going to activate any slip systems. And even if I manage to activate the slip systems, I get shear on parallel planes, and shear on parallel planes is not going to give us ductility. But we could get a situation where every grain and every neighbor grain has a different orientation and it responds differently to the external load. And by that, we could get a good compatibility of deformation of grains and a better ductility. So it makes sense to think about grain refinement. And let's see some of the considerations and also challenges associated with that. If you're dealing with magnesium alloys, let us begin with this one, with magnesium-free alloys. Sorry, with aluminum-free magnesium alloys. If there is no aluminum included in magnesium alloys, we could think about zirconium as being a very useful element. We could use master alloys. These are alloys which have high concentrations of zirconium, and on top of that, some magnesium. So they are zirconium magnesium alloys. We don't want to use pure, sorry, zirconium, not zinc. Zirconium magnesium alloys, because they are more economical than adding pure zirconium. We could use these master alloys, and they are added to the liquid shortly before casting. We are ready to cast. Shortly before that, we add these compounds, and we are going to create some nucleation sites for the solid material. During casting, we get more heterogeneous nucleation sites for the formation of solid phase, and by that, we get grain refinement. More nucleation events would mean that the grain size is going to get refined. So this is one of the solutions for aluminum-free magnesium alloys. As soon as there is no aluminum, we could add zirconium. And indeed, there are also some issues. For instance, one of the issues is the high density of these alloys. Zirconium has a much higher density than magnesium. So it tends to sink down. You're putting some powders or substances, so particles of zirconium master alloy, it tends to go down in the liquid. It tends to settle and sink. And it's related to its high density. And that is going to give us problem in getting a homogeneous nucleation. So we are not effectively using zirconium because it is settling down to the bottom of crucible. So this is one of the challenges. We need to make sure that it remains kind of floated in the liquid during casting. Another challenge is if the alloy contains some iron, it is going to combine with zirconium and give us some intermetallics, right? So this is also something to think about. It makes sense to go to low iron magnesium alloys. So if the amount of iron is reduced, this problem is not going to be a serious one. But if the amount of iron is reduced, we get a problem during casting, during die casting. The dies we are using, they are out of steel. And if magnesium melt doesn't have any iron, it tends to absorb iron from the die. It comes into contact with the surface of die. Die is out of steel. And here we got magnesium melt. And magnesium melt could be thirsty for iron. If it has a very low iron content, it means that it still has some capacity for iron. It tends to absorb iron from the surface of the mold, right? So this could also cause problems. Normally, magnesium alloys have enough iron to make sure that iron from the die material does want to get dissolved in magnesium melt. But if we eliminate iron from liquid melt, then the liquid melt has more capacity to get iron from the mold, and there is a chance of, or the risk of a sticking. So magnesium alloys and mold could get stuck together. And that could create problems during die casting. So during casting in metallic molds out of steels. Good. So that was the option we have with aluminum-free magnesium alloys. Here's an example: pure magnesium without zirconium, and pure magnesium with 1% of zirconium added. We see that it refines the grain size dramatically. Scale bar is not included, but I assume we are talking about the same magnification. So we see the influence of zirconium in reducing grain size. And by the way, I think some of regions of these pure magnesium, we could also see some twinning. Right? It is hard to deal with magnesium alloys. If you would like to prepare specimen for metallography, you have to be very careful. It is very soft. You readily get scratches. It gets deformed at surface. And if you're deforming that, you can probably also activate some of those slip systems and also some of those twinning systems. Right? Deformation is not only by slip, but there are also some twinning systems which could activate it due to plastic deformation. And in this case, plastic deformation is coming from specimen preparation, which makes handling of magnesium alloys quite difficult. If you're dealing with aluminum-containing magnesium alloys, zirconium cannot be used because zirconium has a high affinity with aluminum, and also a high affinity with manganese, right? So if these elements are included, then there is practically no reliable method for grain refinement. right? So what we could do is to aim for high cooling rates. Instead of using a sand mold, we could think about a metallic mold, and also high pressure die casting. It gives a very high cooling rate, and by that we could get grain refinement. Good. Therefore, it matters if you are considering aluminum-free magnesium alloys or aluminum-containing ones. So this method, zirconium, is not going to work for A, Z types of alloys, right? If you got this alloy, for example, due to the presence of aluminum, and these are very important magnesium alloys, we cannot use zirconium as grain refiner. So this one shows the influence of alloying elements. Aluminum is a very important one. So if you want to kind of summarize very roughly the influence of aluminum as an alloying element in magnesium alloys, it increases the strength values, it enhances castability, the liquidus temperature goes down, it becomes easier to cast these alloys. They become even more economical because aluminum is less costly than magnesium a lot of times. Indeed, there are a lot of fluctuations in the magnesium market, depending on the supply from China. But at the moment, we could say that magnesium is the more expensive element, or much more expensive than aluminum. Perhaps we got a factor of 2 between them nowadays. So if you're putting aluminum in magnesium, we are saving costs. Creep strength is it's not going to help with high temperature properties. If you're talking about high temperature properties, we are talking about temperatures like 200, 250 degrees Celsius. These are considered high temperatures for magnesium alloys because we are above 40% of melting point, where creep could come into play. And ductility goes down because by adding aluminum, we are creating some eutectic systems, right? If we get eutectic products, then we are losing our ductility and also reliability, the impact strength. Good. There are new developments, a lot of new developments where people are taking advantage of elements such as alkaline earth metals, metals like calcium, strontium, and also rare earth elements. There are a lot of new developments because these elements are known to primarily enhance the creep strength. We are adding these elements. We could put magnesium alloys in applications where temperatures are kind of raised. So creep resistance is going to get better, and rare earth elements are elements which have a very high solid solubility in magnesium. For instance, cerium, neodymium, yttrium have high solid solubilities. We could take advantage of solid solution strengthening, and also these are slow diffusers. And by slowing down diffusion, we could expect enhancement of creep properties. Good, but it's going to add to the price, right? Rare earth elements, as the name implies, they are rare and therefore expensive, and we must consider the higher price of these alloys. Castability issues might exist, right? They also tend to oxidize very quickly, and it could create problems during casting. And also ductility. If we get second phases, some compounds or oxides inclusions due to the addition of these reactive elements, then we could also lose reliability or lose ductility. Good. Let us now review some applications of magnesium alloys very quickly. These are some examples of alloys, and I see majority of them, or all of them, I guess, have been produced by die casting. In this case, high pressure die casting. It's a very common technique. We reviewed that in the context of aluminum alloys. A lot of times the housings, cases, where we don't have a critical condition, so it is not going to get critically loaded. Now, there are indeed loads, but it makes sense because of weight reduction to switch from aluminum alloys to zinc alloys, especially these ones. They are very well established. They are very readily available. And a lot of alloys are out of these sort of semi-chemical composition, 9% aluminum and 1% of zinc. This is a seat frame, 2 kilograms. We could get lightweight. It could also be used for the manufacture of seats in the aerospace industry. Requirements are kind of more strict in the aerospace industry. So if there must be safer, right? Risk of fire must be as low as possible, but it could also be applied to the aerospace industry. Here's a thixomolded magnesium alloy, and thixomolding or thixoforming are processes where we deal with material in the semi-solid state at temperatures between solidus temperature and liquidus temperature, where we get a mix of solid and liquid phases. So this is a thixomolded part. They offer good quality because temperatures are lower. Solidification shrinkage is going to be smaller compared to where we begin from a fully liquid state, right? Then we expect to have a larger contraction, and we could get some shrinkage porosity in the final product. By dealing in the semi-solid state, we could expect an enhancement of properties. So steering wheel, cell phone case, and also the chassis could be out of magnesium. Again, another frame out of magnesium alloys. These are some common applications. Now, if you look at the automotive market, on average, we could say that there is almost 5 kilograms of magnesium per vehicle. compared to the aluminum. Aluminum is being used in much higher quantities, almost 120 kilograms. So we can also see the difference here, right? They are lightweight, but there must be a good justification for the use of magnesium. It must not be a critically loaded part. Then we could think about switching from aluminum to magnesium. So there has been a lot of increase. So in the past, so perhaps 20 years back, it was even less than 5 kilograms. Now, automotive industry is thinking about magnesium, whereas in the aerospace industry, they are using less and less of magnesium, because there they could think about solutions based on fibers, right? Carbon fibers and composite materials. Whereas those solutions are probably too expensive for the automotive industry. They could be happy with a magnesium alloy. So in magnesium, in the automotive industry, the trends are such that we see an annual increase in the amount of magnesium used in the car industry, whereas in the aerospace, that would be the next slide, we see a decline in the fraction of magnesium. There are indeed a lot of components in the aerospace industry out of magnesium, a very large number, perhaps hundreds of parts per airplane are still out of magnesium alloys, but there are tiny casings and frames, non-critical parts, where magnesium could still be used. Here are some examples. This is a die-cast helicopter component, or two components, out of AM50 alloys. Again, we could read the chemical composition. So it has 5% of aluminum and a little bit of manganese is there. This is a component for a helicopter gear case. So this is a huge component. After casting, 133 kilograms. If it's finished machined, after machining, the weight reduces to 111 kilograms. So a lot of potential to achieve lightweighting for this huge component in a helicopter, right? And it is an alloy which includes zinc, rare earth elements, zirconium are there, and we could use the lightweight potential here. In Russia, there were initially a lot of use of magnesium alloys in the Tupolev airplanes. And here's an example of this relatively old model. Regions marked in red, they were made out of magnesium alloy. So if you find this one, if I look at it, this was TU-134. There were almost 800 kilograms of magnesium used in this airplane. But with time, the newer models, they are using less and less of magnesium. But still, a large number of components are out of magnesium alloys. But if you just compare to the older time, we see a decline, and that is related to more attractive options. Here's another example, an interesting one, an old airplane. Actually, US started to make this one during the World War. It was finished at that time, shortly after the First World War. The consideration of the US was to make an airplane which is very lightweight. It could fly from the US to Britain. They wanted to support Britain against Germany during the Second World War, and it had to fly to Great Britain and get back, right? It must be chosen out of a material which is very lightweight, right? There they put almost 9 tons of magnesium in this old airplane, right? A lot of sheet out of magnesium and a lot of forging parts, and also some other probably die cast parts and so on were also included. Good. I would like to also briefly cover some other applications where magnesium could be used based on its corrosion properties. And one of those applications is used as a biodegradable grade. It has a low corrosion resistance. It corrodes very easily in contact with liquids in our body. So there is a concept where magnesium alloys are used as implants, which are serving a purpose temporarily inside our body, and after a while they disappear because they start to corrode. And here are some examples. For example, the stents. If we have an application where a blood vessel needs to be kept open for a while, and after a while it's not needed anymore, we could think about magnesium alloys. And these are alloys where we could put yttrium, rare earth elements, zirconium. We need to make sure that the elements we put in these applications, these are applications in our body, they must be biocompatible elements, right? So these must be elements which do not interfere with the metabolism of our body. So they must be elements which are necessary. And magnesium is an element which is necessary for the body metabolism. Daily, we require to get something like 250 to 420 milligrams of magnesium. And it is possible to think about using magnesium as implants. If there is a fracture of bone, for instance, the nails, which could be used in order to keep bones together for a certain amount of time, perhaps for 1 year until healing occurs, they could be out of magnesium alloys, and you could save a second operation. If you make it out of titanium, you might want to take it out with a second operation. You don't want to have titanium in your body, but you could make it out of magnesium and it will disappear automatically after a while. One of the problems is that during corrosion of magnesium, some hydrogen is released, and this is going to cause problem, right? We don't want to have release of hydrogen inside our body, and this is one of the challenges associated with these alloys. But there are developments, some alloys which are having a relatively high corrosion resistance, so they don't corrode very fast. If they corrode very fast, they release hydrogen within a short amount of time, and that could create a dangerous situation. But by increasing corrosion resistance, we could expect better properties. And these commercial alloys, we could assume they are the ones with a relatively high corrosion resistance. Pure magnesium is going to disappear very quickly, and that's why a lot of new developments are not pure magnesium. They have alloying elements to increase the corrosion resistance. And this is the final slide. Magnesium is an element which is sitting at the bottom of electromotive series. It has a very low standard potential compared to majority of metals and also compared to steels. It has a much lower potential compared to pure iron. With iron, we got minus 440 millivolts. With magnesium, we got almost close to minus 3 volts. It makes it possible to use magnesium as sacrificial anode for protection of steel structures. If we want, for example, to protect the surface of a ship, the ship hull, against corrosion in seawater, we could use anodes out of magnesium alloys. For example, probably these are also this very widely known grade of magnesium. We could use them in order to protect steel structures from corrosion. In water heater, in every household, probably there are these water heaters where we can protect them against corrosion by using anodes out of either magnesium or aluminum is another option, which could be used sacrificial anodes. And for pipelines also, one option would be to think about magnesium for corrosion protection.